Good day, everyone. I am the student 17 named Melissa A. Cojado, and my report is all about design flood discharge, part 1. Flood design discharge determination is a very significant decision in water-related structure planning and construction. Water structures that requires proper flood design discharge are canals, derivation, tunnels, dams, culverts, bridges, and levees. Various scientific probability and statistical methods are used for determining the worst accurate design flood quantity. Due to climate change impact, time series records that are taken into consideration in any flood discharge design also change, and therefore, it is necessary to revise the design quantities continuously for at least every 5 years or 10 years periods. The climate, land use, vegetation, and geomorphological changes bring significant dynamic uncertainties into the decisions and contribute severely to the flood risk calculation procedures, such as first is a design discharge definition. The flood design discharge for water structures has numerous definitions, and most significant are the following. Design structures is the maximum flood that any hydraulic cross-section allows to pass safely without inundation problems on the channel banks. It is the amount of discharge that is calculated by taking into consideration the allowable and tolerable risk level. It is the flood discharge that can be sustainable by hydraulic structure without any significant damage. It is the maximum past flood discharge that is selected for safety design and evolution of the water structure. And lastly, it is based either on the entire flood hydrograph as the values of discharge change along time or the peak discharge of the flood hydrograph. The second one is the design discharge choice. Determine the design discharge for streams for a particular recurrence interval. Establishing a return period provides a benchmark of the relative risk to be attached to any particular design. Probable maximum flood, or PMF, is according to the U.S. Federal Energy Regulations Commission's 2001, the PMF is the theoretically largest flood resulting from a combination of the most extreme combinations of meteorological and hydrological conditions based on the rainfall and geomorphological in a particular drainage area. Standard Project Flood, or SPF. It is a similar concept is a standard project flood. In general, the magnitude of the standard project flood is about half that of probable maximum flood. Depending on the reasonable characteristics of the region and drainage basin, it is the discharge amount that results from the most severe meteorological and hydrological conditions. Computation should be taken as the largest storm record in the drainage basin region. Flood of a specific return period. In this case, flood frequency analysis is the basis of design flood calculation from the annual, partial, or hybrid past flood values of adequate lengths. If there is not adequate flood data, then the frequency analysis of available storm rainfall data helps to calculate the storm of a particular frequency. This alternative leads to flood discharge usually with a return period greater than the storm itself. IDF, or intensity duration frequency curves. IDF is the mathematical functions that relates the rainfall intensity with its duration and frequency of occurrence. IDF curves are obtained through frequency analysis of rainfall observation. IDF curves are also necessary for efficient operation of energy dissipation system by considering a design discharge which may be lower than the IDF for dam safety. The use of this flood discharge with standard specification or other factors affects the performance and the energy dissipation arrangement in the most efficient manner. IDF curves are also used for checking extent of upstream submergence, which depends on prevailing local conditions such as type of property and efforts of the submergence for very important water structures like powerhouse mines. SPF or PMF levels are helpful to determine submergence effects. In general, for land and built-up property acquisition, a 25 years or 50 years design flood is recommended for adaptation respectively. Limitation of calculations. Although theoretically sound, both PMF and SPF methodologies have restrictive boundaries. And one, in many parts of the world, long-term hydrometeorological data are not available for reliable design storm parameter estimations. Two, unfortunately, physical rainfall modeling procedures to compute PMP is not fully available, and accordingly, as available today, the rainfall process knowledge and information have severe limitation. Number three, currently, the historical storm maximization for probable maximum favorable conditions is based on the surface dew point data, which cannot represent moisture availability correct enough in the upper atmosphere. Number four, the drainage areas are not covered by self-recording rain gauges that reflect the historical individual thunderstorms data. Five, there are a set of assumptions in the unit hydrograph theory which are not valid in practical applications except in the average. And number six is the derivation of unit hydrographs suffers from the good quality and inadequate data quality. And the third flood risk calculation procedure is a discharge magnitude classification. Hydrological design discharge is the amount of discharge calculation based on a certain level of risk. The design discharge can be calculated under a set of assumptions and prevailing conditions, all of which can be taken into consideration in an effective planning, management, and mitigation principles. It is also important not to select big designs discharge that may cost high economic investments or small discharge quantities to give way to more dangerous situation. However, small design discharge may be subjected to several hazardous occurrences during its economic life which may lead to destruction of structure. Depending on the discharge magnitude, it is possible to classify floods by the following. There are three classifications of floods, which is the first is the common flood, standard project flood, and infrequent. Common floods, this may overtop the water structure during its economic life. And the standard project flood, it is decided by consideration of the whole drainage basin response to an extreme rainfall event. This discharge can overtop the reliable capacity of the water structures once or twice. And lastly is the infrequent floods. These are not so much dangerous and they have magnitudes between the SPF and the PMF. In order to make the design of the PMF planning, it is necessary to have economic opportunities and the risk level that will be taken into consideration during the functioning life of water structures. The risk level decision must be assumed at the beginning of all the planning and project design. There is a direct relationship between the risk level and the economy of the project. Any decrease in the risks implies increase in the project design flood discharge. In general, one can expect at least the following three functions of the water structure. First is the reliability performance. Second is the low economic cost. And the third one is the function throughout the design life with the least hazardous situations. And the fourth flood risk calculation procedure is a design flood prediction. Unfortunately, so far there is not an accurate formulation to calculate the rainfall intensity for precise estimation of flood design discharge. These are approximate formulations, whatever the availability of the data, which lead to approximate evaluation of flood discharge and hazard assessment. The recurrence intervals for culverts, small bridges, and the drainage structures in the secondary highway ranges from 5 to 100 years. The most common recurrence interval for these structures is 25 years. The most common recurrence interval for the larger or more important structures is 50 years. Sometimes, to be on the reliable side, in spite of the life of 100 years or 200 years, engineers may also take into account 500 years life flood design. For flood discharge, there are different approaches, each with additional complement to others. Flood discharge estimations by means of empirical formulations that are based on gained experience in a region. Flood estimation by use of envelope curves determined based on previous flood discharges. Application of rational and logical formulations. Probability and statistical approaches also provide theoretically methodologies for flood discharge estimation, and unit hydrographs are other means that helps to estimate flood discharge. And the fifth one that have the flood risk calculation procedure is the flood design discharge calculation. There are many flood peak discharge estimations formulations that have been developed over the last 150 years. Some of them are much localized, but others have a wider applicability all over the world. However, they must be applied with great prudence and prior to the application. The basic assumption must be verified as much as possible. Unfortunately, none of them provide precise result even for the applicable areas, and therefore probability, statistical, and risk limits must be taken into considerations. The uncertainty is due to the fact that the flood peak discharge depends on many factors, and it is not possible to take all of them into considerations in one formulation. In order to know the maximum water level, the past flood marks on ancient monuments, bridges, sites along river banks can be observed by some persons who live nearly the bank of the river. It is possible to obtain the following geometric measurements from a distinctive cross-section with flood marks, which is the water flow area, A, through the cross-section, and the weighted perimeter length, P, and the radius of influence R, which is the ratio of the rational area A to the weighted perimeter P. It is possible to measure the cross-section slope S by considering a certain distance toward upstream and downstream between 2 points. Each one of them may be about 50 or 100 meters away from the cross-sections along the main channel. All these quantities can be substituted into Manning's or Cheesy equations with the determinations of roughness coefficient, and then the resulting flood discharge can be determined empirically. Apart from this calculation method, there are several other empirical formulations for flood discharge calculations. First is the catchment area-based formulations. These take into consideration the catchment area A without any rainfall quantity concern, and the peak flood discharge can be calculated as Q is equal to Ca to the power of n, where C is the flood coefficient and n is referred to as the flood index, both of which depends on a set of factors such as the catchment size, shape, location, and topographic feature, in addition to some rainfall descriptions as the duration and storm distribution pattern. And the following are the alternatives for this formula. First is the Deakin formulation from 1985. There is a nonlinear relationship between peak discharge QP and the drainage area A through Deakin's constant CD, which assumes values between 5 and 30. The formula is QP is equal to CDA to the power of 3/4. The peak discharge result in cubic meter per second provided that the area is in square kilometers. And the second one is the Reeve formulation from 1884, which is QP is equal to CRA to the power of 2/3. The peak discharge QP is obtained in meter cube per second, provided that the drainage area is in kilometers squared. Reeve's expression is developed originally for Tamil Nadu region and also for parts of Karnataka and Andhra Pradesh. Reeve recommends the coefficient values as 6.8 for drainage areas within 80 km from the east coast, 8.5 for areas that are 80 to 60 kilometers away from the same coast, and finally 10.2 for limited areas near hills. Mayer and others from 2009 formulations. It is also developed for the USA drainage basins, which expresses the flood peak discharge as QP is equal to 177 P the square root A in cubics, where P has a value of unity for stream that has the greatest flood flow of the area. For any other stream, P is the fractions for the flood flow of stream. For different stream, values of P vary from 0.002 to 1.0, usually taken as 1. Jarvis formulation. This is very similar to the previous formulation and comparatively simpler than it. The formula is Cp is equal to Cs the square root of A, where Cj varies between 1.77 and 177. Qp is in meter cube per second if the drainage area is substituted in kilometer squared. And the last formulation is the Fuller from 1914. This is also empirical formula, which relates the peak discharge to the drainage basin area and is included also the flood frequency. It is developed for the USA typical drainage basins. Its expression is given as QP is equal to CFA to the power of negative 0.8 times 1 plus 0.8 log T, where QP is the peak discharge with maximum 24-hour flood with a frequency of T years, and it has cubic meter per second dimensions with A in kilometers squared, and the Fuller constant values between 0.18 and 1.88.